How can sound follow all the laws of reflection that light does? Aren't they different? One is a physical wave, the other isn't. And yet, both of them follow all the laws of reflection. It seems like as if when sound reflects, it's almost completely identical to a reflection occurred through light. How does it happen? To understand that, we must first understand how does sound propagate. Once we zoom in on the particles, we can see that they create a mechanical oscillating wave. That means the particles are going constantly back and forth. The particles of the wave collectively work like this to show us a pressure wave, as you can see over here. So, what happens when those particles hit an object? By Newton's third law, the object executes an equal and opposite force on the particles, and then they go backward. So, when the particles of the wave are moving forward and hit an object, they execute a force on it. And then, after that, by Newton's third law, when the object executes an equal and opposite force on their particles, they move backwards. This is somewhat how the total propagation of the entire wave changes. After applying the force, when it faces an equal and opposite force, the whole propagation goes backwards. Now that we have understood how sound propagates and how it reflects via Newton's third law of motion, let's get back at our original scenario. So, when the incident wave comes and strikes our mirror, the force it applies can be broken down as a sum of two vectors, one being parallel and the other being perpendicular. The perpendicular force is going to be the only force which our reflecting object experiences. Hence, by Newton's third law of motion, the reflecting force which will be equal and opposite is also going to be only for the perpendicular force, and the parallel component stays the same. Hence, this resultant trajectory of the particles is going to be the sum of these two vectors. Now, let's imagine a triangle formed by the resultant perpendicular force, the incident wave, and the parallel component. They form a right angle triangle. Relative to angle theta, which is our incident angle, b is the height, v is the hypotenuse, and h is the adjacent. Sine is equal to height by hypotenuse, which will be b by v. When we multiply b by v itself, we get our original height, which is b itself. Now, how does this apply to our case? Since both b dash and b are the same vector, both of them have the same sign value, and hence we can conclude that both of these signs are equal, and signs are always equal when the angle formed between them is equal. Hence, angle of incidence is equal to angle of reflection. Now, what about the other law of reflection, that all the objects involved in it remain in the same plane? This works out for sound as well, because each individual particle in the longitudinal wave undergoes this process until the entire sound wave reflects back up. So, to sum it all up, sound waves reflect because of Newton's third law of motion. Now, when the incident wave strikes the mirror, it can be broken down into its vector products, and Newton's third law of motion, the perpendicular vector product is the one being reflected, and hence the reflected wave is sum of the parallel and the perpendicular component, meaning all the properties that we get of the sound wave is just a consequence of how vectors operate and Newton's third law of motion. Thanks for watching this video. I really hope you enjoyed it and understood the concept clearly. Make sure to like, share and subscribe, and if you have any doubts, feel free to comment below.